So welcome. So this is the second video on this is the this first video on this bit, and we're basically going to do talk about frictional force and normal force, and then we're going to do statics and dynamics in more detail and apparent way at the end. So friction force and normal force. If I have things sitting on a slope, then of course for every action force, that's the force of the weight on the slope, then we have the force of the slope on the weight. So we have those two balancing each other if it's in equilibrium. And well, there's action-reaction pair. So then for this guy, then I can divide it up into two components. And I choose to make one component along the slope, either up the slope or down the slope. And the other component is going to be perpendicular to the slope. So I always break up my reaction force into two components. A part which is along the slope, and I call that the frictional force. And a part that is perpendicular to the slope, and I call that the normal force. Not meaning usual. Normal does not mean the usual. It's mathematical. It means at 90 degrees too. It's just one of those arcane things that the math people use. Normal means at 90 degrees too. So the normal force is the component of the reaction force that is perpendicular to the surface, and the friction force is the component of the reaction force that is in the plane of the surface. So let's do an example. A 2 kilogram block is stationary on an inclined frictional slope. What is the normal force? So little squares, big arrows. Most people do big squares and little arrows. Do a big arrow. This is going to be down here. And this is going to be 2 kilograms. So that's going to be 20 newtons. So there's going to be a normal component, and there's going to be a frictional component. And I only am concerned in finding the normal force. So, if I'm only concerned in finding the normal force, draw your axis perpendicular to the frictional force. So draw this axis that is perpendicular to the frictional force. And say, well, this is actually in that plane, so it's its own component. Then look down here. That's 30, then that's 30. Can you see that? If that's 30, that's 60. If that's 60, that's 30. Yeah? So this here would be 20 cosine 30. 20, because it's the magnitude, it's the hypotenuse. And the cosine, remember that thing about if we've got one and we want the other and we're using the angle in between, it's a cosine? Well, I've got the hypotenuse and I want the adjacent, so it's the cosine of the angle in between, which is a 30. Okay. One of these is positive. Sorry, I'm losing my pen. In fact, I've lost my pen. Well, that's not good. Bear with me a second. I wonder if it's... Well, that's a real blow. Let's try unplugging it. Now you're back. Okay. So then I say the sum of the forces along the purple line equals 0. Let's call this the positive end. Let's call this the negative end. I'm going to say plus Fn added to minus 20 cosine 30 is equal to 0. So Fn is equal to 20 cosine 30. So Fn is equal to 20 cosine 30, 20 cosine 30, and that's going to be 17.32. And hopefully that's one of the choices. Yep, 17.32. So I drew a diagram. And then I identified the thing I'm not interested in. And I drew an axis at 90 degrees to it. And then I worked out my components of the two remaining forces in that direction. And then I did my math. Yeah. Okay. Can you do the same and tell me what the frictional force is, please? Actually, we've only got, what, 10 minutes? Okay, let me do this one. We've only got 10 minutes. This is again 2 kilograms, so that's going to be 20 newtons. And this is 30 degrees. How do I know that FF is pointing up the slope? Because the natural tendency is the block is to slide down the slope. So if it's not sliding down, it's stationary. If it's not sliding down, the friction must be up. And then come along and get a different colored pen. I'm not interested in, I want to find the force of friction, so I'm not interested in that. So I draw my line perpendicular to it. This is its own component. So this is FF is its own component. This down here would be 20. If that's 30, then that's 60. That's 30. This would be 20 sine 30. That's going to be a negative because that's my negative end. That's my positive end. I just decided that. You can decide it either way, you'll still get the right answer. The sum of the forces, red line, equals 0 plus FF added to minus 20 sine 30 is equal to 0. FF is equal to 20 sine 30. FF is equal to 10 newtons. Positive 10. It's pointed in the positive direction. Yep.
How did you get 30?
Oh, if that's 30,
Okay.
then that's going to be 60.
Right. So,
If that's 60, this is 30. It's two triangles. There's the first triangle is that guy. Yeah? And then second triangle is that guy. Yeah. So if that's 30, that's 60, because that's 90. And then for that one, if that's 60, that's 30. And can you see how actually drawing a big angle and a little angle, once you're happy with that, you just look and go, oh, little 30, little 30. Whereas if I drew them at 45, it could be anything. So it's really useful to have a decent diagram at this stage.
using the sign because it's along the hill
Yeah,
itself.
I want that.
Right.
So that's my opposite,
Right.
and that's what I got.
Right.
and that's the hypotenuse. So I want that, and I got that, and I chose not to use the angle in between. It would have been 20 cosine 60,
Gotcha.
which is the same as 20 sine 30. Yep, cool. Yeah. Okay. Friction is a thing in its own right. It's not just a component. There is a thing called friction. It is a thing in its own right. So what is it? It's when the two surfaces enmesh. And if I imagine a surface near the top, if I imagine sitting a block onto a surface, although it might look smooth, microscopically there's a whole bunch of valleys and cliffs, and so if I let the thing sit there, it's pretty well enmeshed, and as I pull it to the side, it's got to kind of work its way out. And once it's free, it'll bounce over the top, but it won't be as enmeshed as when it's sitting there. So if I plot a graph of applied force, that's my sideways pulling force, versus the frictional force, that's what the thing's resisting with. What I see is, before it starts moving, I'm making up the numbers, but take the principle. If I apply 1 Newton, it resists by 1 Newton. If I apply 2 Newtons, it resists by 2 Newtons. If I apply 3 Newtons, it resists by 3 Newtons. If I apply 3.5 Newtons, it resists by 3.5 Newtons. If I apply 3.5 and a bit, it starts to slide. And the trick is, it doesn't slide off at 3.5 and a bit Newtons. It comes down a bit. It's less than 3.5 because you're not enmeshed. 3.5 when you're enmeshed is what it takes to get it out. Once you're sliding over the top, it's not as significant. So it takes less to keep it going. Okay? So when it's moving, your frictional force might be only 3 Newtons. When you're stationary, it could be anything up to, in this case, 3.5. So we refer to static friction and kinetic friction. And you don't always know the value for the static frictional force. It depends how much you're applying to it. But it'll balance what you're applying because it's static. But once you're moving, it pretty well goes to a set value. And, you know, it doesn't matter how fast you move, it's going to be that same set value. We can define the ratio between the applied force and the frictional force. Well, actually, no. We really define the frictional force depends upon the amount of enmeshment. And that's a function of, you know, how much you enmesh. And you might think that's a function of weight. But the frictional force is dependent upon the amount of enmeshment under all circumstances. And although the weight here is giving me a fair idea of how much enmeshment there is, here the weight's not giving me a good idea of how much enmeshment there is. It's much better to use the normal force. So we say that the frictional force is a function of the normal force, not the weight. And it's a numerical value. So basically, we have what was called a coefficient of friction. The coefficient of friction can be anything from 0, or maybe just a little bit above 0, to 1.5, you know, something like that. If it's near 0, it's a really smooth interface. If it's 1.5, it's really tacky. You know. If it's 1.5 on a flat surface, it means that it's harder to push it sideways than it is to pick it up. That's a really tacky surface. That's a pretty friction-filled surface. For kinetic, because it's a constant value, we just say, well, it's equal to this mu k times Fn. And for statics, it's less than or equal to this mu Mu is just like a U with a little tail on it. We call it a mu. Like a marshmallow, mu. Mu K. So we call it mu S and mu K. Okay. And we can look these up in books. So there's a thing called the National Institute of Science and Technology. In Britain, it's called the National Physical Laboratory. And these are organizations that are dedicated to measuring stuff for engineers, basically. And they measure the speed of light, and they do all these kind of things, you know. And so they basically have projects where they'll measure the static friction for a whole bunch of interfaces. It's not just about the table, and it's not just about the block. It's about the combination of the two. And if I invent a new material, suppose I invent some exotic compound, then at some point, probably somebody from NIST is going to ask if they can have a sample of it, and then they're going to do an experiment to measure its static friction. It's going to go into the book, the engineer's handbook, and then people will, if they want to use that material with various other combinations, they'll be able to look it up. It's amazing. It's got wood on wood. It's got oak on elm. It's got willow on cedar, because different engineers want to know these things. What engineers are looking for are things with very high coefficients of friction, because they're very friction filled, and things with very low coefficients of friction because they're very smooth. The problem you run into is that that's what engineers, this is the art of engineering. I can pick a pair of materials that have a very low coefficient of friction, but there's also where, how long-lived is that surface. And I can have combinations of materials that are very frictionless but wear like crazy. And so it's going to degrade in no time. On the other hand, I can have... So there's trade-offs that engineers make. If you think about it, an automobile engine has not changed in principle in the last, 80 years, 90 years, 100 years, something like that. In my generation, I would never turn off an engine. Once my car began, I drove to where I was going, because my car was that little bit older, and once I turned it off, I wasn't 100% sure it was going to start. So you learn not to turn your engine off. And now they have hybrids that the car turns the engine off. You know, when you don't, it just turns the engine off. First time I saw that, I thought, that's crazy. You know, it's like, why are you doing that? And the difference is reliability. And the reliability is not because they've invented some new kind of engine. It's because really they've made the materials so reliable and so well designed that you can make now electronics out of bits of silicon that just you can bang around and it makes no difference. You couldn't do that with the old tube type things. And, you know, now, until relatively recently, I would take my car in to be serviced every 3,000 miles. I was always late, so I tended to ruin engines. That's, you know, I didn't get many miles out of them because I was always going to do it next week. And now, what is it? I can get probably, 10,000 miles out of my car without being... That's material science. That's not fundamentally changing science. That's changing the materials we use for science. And so that's why that's a whole fascinating region in itself. We'll stop here and we'll continue next time.